Good day, viewers all over the world. Today, we want to look at integrating factors. That is, in our last video, we talked about exact differential equations. That is, and the test for exactness simply means that when you differentiate the x or comma y is what we have beside the y, then n x comma y is what we have beside the y. So when you differentiate the the y, and if it's equal to the the x, we say that such a differential equation is exact. But under this concept where we have integrating factors, it is possible to transform a differential equation that is not exact. That is, when you are given a differential equation that is not exact, we can actually transform that differential equation to become an exact differential equation by introducing integrating factor. That is, if you have such equations, you just multiply through by the integrating factors. Then such equation that is not exact can actually become exact by the time we follow the process. Some of the common integrating factors are displayed in the table below. Of course, when you have standard, if you get standard textbook on differential equations, we are going to have these tables there. In the table, there are more than this, so I just try to select maybe 5 of these, then and so on. So if this is the group of terms, if this is the form of differential equations, then you can apply this integrating factor, which is minus 1 by s squared. By the time you transform then the exact differentials will be in this form. So once you multiply a differential equation, given the differential equation by the integrating factor, we are going to transform that differential equation that is not exact. It becomes exact. Then we are going to solve the given differential equations. So these are some of the examples of differential equations that are not exact, that has been transformed to an exact differential equations. So let's give example. We're going to give example just to be able to know how to solve differential equations that are not exact. And once we introduce integrating factor, it becomes exact. And the method of resolution, how do we solve such differential equations? That is what we want to do. I think, of course, the differential equation must be first order differential equations. So we are talking about first order differential equations there. First order differential equations. So let's say example. Let's start with the first one. Example. We are to determine whether minus 1 over s squared is an integrating factor. Integrating factor for the differential equations y dx minus x dy equal to 0. Okay, this is the A part of the person. This person is 2. Then the second one, we have to solve y dx minus x dy equal to 0. So we have to solve the differential equations. So this is what we are given, and this is what we are required to find. So how do we go about this? So we want to check if this differential equation, if minus 1 over s squared is an integrating factor for the differential equation. This is the differential equation. Y dx minus x dy equals 0. That's the differential equation. So how do we check if this is the integrating factor? The first step is that we are going to use that if we are given a differential equation that is not exact, I want to transform that differential equation to exact differential equation. You multiply it through by the integrating factor. Now test for exactness. So if you do that here, you are given, want to check if minus 1 over s squared, you are going to multiply through by this. Of course, when you use this to multiply this, it will be 0. Anything multiplied by 0 is 0, so we don't have any problem. Then from here, we have minus y over s squared dx minus 1 over x, this will be plus 1 over x dy equal to 0. Anything you multiply by 0 is still retain its value. So from here, what we have beside dx will be m of x comma y, and it's given us minus y all over x squared. Then what we have beside the y will be n of x comma y, and it's given us 1 over x. That's what we have. So for us to test for exactness, we have to differentiate m partially with respect to y, the m the y. That's what we are going to do. We say the m the y. If we differentiate this, what are we going to get? We are going to have minus 1 over x squared. Then we also differentiate n partially, the m the x. Of course, this is x raised power minus 1. By the time you differentiate it, we have minus x raised power minus 2. That will be minus 1 over x squared. That's what we are going to get if you do that. If you compare the two results now, if you compare the two results, you realize that they are the same. We realize that they are the same. That is, the m, the y is same thing as the n, the x. So, and what is the implication of that? So, it shows that we have been able to transform this differential equation to become, because this is the condition for exactness. If you check the video on exactness, so we have been able to show that it is exact. It is exact. So we have to determine whether this integrating factor is, we have to determine whether this integrating factor is an integrating factor for the differential equation. So when we use this integrating factor to multiply this differential equation, we are able to test for exactness. So it shows that that integrating factor, that value minus 1 over x squared, is an integrating factor for the differential equation. So that's the first part of the question. So we have been able to do that. Then we have to solve. How do we solve this? If you check the table, from the table, there are standard tables. So from that table, if you check the table, from the table, what can you say? From the table, you realize that if you have x dy minus y dx all over x squared is given as the y all over x, okay, and of course it's equal to 0. That is what we have, because if you use this to multiply this is what you are going to get here. This is the same thing as this, okay. Then what do we do here? That is the transformation. So by direct integration here, this is the y over x. If we differentiate this directly, what are we going to get? By direct integration, what are we going to get here? This is the y over x. When we introduce integration, at the end of the day, we are going to have y all over c to be y all over x to be equal to c. Because when you have that, if you introduce the integral side, you take care of that day, then the right hand side is going to give us a constant. Integration of a constant is that will give us a constant. That's what we are going to get. Then if you cross multiply, y will be equal to cx. This is what we are going to get as the solution. This is what we are going to get as the solution. Okay? That's what we are going to get as the solution. That's what we are going to get as the solution. And if you don't want to stop that way, we can actually go ahead and alternatively, we can also solve it using this method. We can say alternatively. But if you don't know the values that we have in that standard table, then there's need for us to follow this process. We follow the normal process of integrating. That is, we say, or if we don't know this value from the table, we say alternatively, what will happen? We know that the g, we now want to solve this problem. Since we now know that we have transformed this problem to become an exact differential equation. We go ahead and use the method of differential equation. The g, the x, will be equal to m of x comma y, which is same thing as, if you check the problem, it's same thing as minus y all over x squared. That is what we have beside the x. Okay, that's what we are going to get. That's what we have. Then n, this is the g, the x. Then we have n of x comma y. From that question is given as 1 all over x, and of course this is the same thing as the g, the y. That's what that one will give us. So what do we normally do when we have exact differential equation? We are going to integrate. So we can call this This is the first one. This first one now, the G, the S, we say integrating both sides with respect to S. That is this first one, the G, the S. If we integrate both sides with respect to S, what are we going to get? Of course, we are going to have G of S comma Y. When we integrate the G, the X, this is what we are going to get. Will be equal to, when we integrate this with respect to S, of course, S will come up. We have it to be X raised power minus 2. That will be minus 2 plus 1 all over minus 2 plus 1. Then this will be positive. This is going to give us Y all over X plus H of Y, equation 1. I want to follow the normal method of solving exact differential equation. You locate the G, the S, which same as M S comma Y. Then the other one is the G, the Y, same thing as N comma S. So you integrate both sides of this, the G, the X, which is M, with respect to X, we generate the first equation. Then once we generate the equation, we now say differentiating. We go ahead and differentiate that equation 1. Differentiating equation 1 with respect to Y. When we differentiate this with respect to Y, what are we expected to get? When we differentiate equation 1 with respect to Y, at the end of the day, what are we going to get? If we differentiate it, then we have the G, the Y, to be equal to, when we differentiate this with respect to Y, we are going to have this to be 1 all over X plus H prime of Y. Then that is equation 2. So what can we say about equation 1 and equation 2? When we solve this, the problem is that when we solve this differential equation using the table, when we know the value of the table, just integrate. We solve it by direct integration. Our value, I want us to know the value. The answer is Y is equal to CX. That's the solution. So when we are now using the normal process, are we going to get the same thing? That's what we want to check. Okay. So differentiating equation 1 with respect to Y, we are able to get equation 2. So then from equation 2 now, we now say equate equation 2. Equate equation 2 and N of X comma Y. That is N of X comma Y is 1 all over S. Is the G, the Y. This equation 2 is also the G, the Y. When we equate the two, what are we going to get? We have 1 all over X plus H prime of Y will be equal to 1 all over X. That's what we are going to get. Okay? And at the end of the day, H prime of Y will be equal to 0 because 1 over X minus 1 over X will be equal to 0. So that's what we are going to get. That's equation 3. So how do we now solve this equation 3? When we integrate this equation 3, let's integrate equation 3 with respect to Y. What are we going to get? Integrating equation 3 with respect to Y. What are we going to get? Then we are going to have H prime of H of Y to be equal to 0. So that's what we are going to get. Okay. When we integrate equation 3 with respect to Y, we are going to have H to be equal to C1. Then if we substitute H of Y back to equation 1, what are we going to get? Okay. So from equation 1, so G of X comma Y will now be equal to Y all over X plus, instead of H of Y here, we change it to C1. Then at the end of the day, what do we do here? When you want to solve this problem, when you want to solve the problem under the exact differential equation, this will be equal to C. That is the normal standard under the differential equation. Then at the end of the day, we have Y all over X to be equal to C minus C1. We can call C minus C1. We can call C1. We can say let's. C and C1. They are all integrated arbitrary constant, so it does not matter. We can say Y all over S is equal to maybe C2, where C2 is equal to C minus C1. They are arbitrary constants. So when we cross multiply here, we get Y to be equal to C2X, which is the same thing as the solution that we got when we do direct integration. Okay. So if you are given any problem that is not exact, the only way to transform that differential equation to exact is to introduce integrative factor into that differential equation. But in this question now, we are given the particular integrative factor that we actually go ahead and do the test for exactness. When we introduce it, we use the integrative factor to multiply the differential equation. We realize that the differential equation has been transformed to exact differential equation. Then, so some of us that are, if you are familiar with the standard table, you can get the table from any standard textbook, differential equation textbooks. But if you don't know what the standard table contains, once you are sure that differential equation has become an exact differential equation, just go ahead and solve that differential equation using this exact method. But it's a longer process compared to when you are sure, when you know the value from the standard table. So you realize that at the end of the day, we were able to get the same answer when we pick figures from standard table, and when we decide to solve using the normal process, we arrive at the same answer. So thank you.